Hello. It's late again a bit. What am I doing? um, sorted. Range length equals. That's correct, right? So like the more we put things into this subarray, like the bitwise n decreases. So it's like a standard two-pointer. Or just we want the longest. So first of all, the max bitwise n is the bitwise n of some number. So like and actually I'm thinking, is it true that we're just like returning the length of the longest segment of that number? Because yeah, if it's something else, it necessarily decreases it. Otherwise, like it has to be larger than it so that the bitwise n doesn't decrease it, which contradicts the fact that, yeah. Something wrong with my desk? In the positive integer k. So like I is something within this range, and I is called good if So we can filter out all the index meeting this condition in one row, like in one pass, and also for this in one pass, and then we take the intersection. So for that, we just break at the decreasing part, like do I need a Q to do that? I think so. I'm going to write a wrapper class to make this simpler. So what this helper function does is it returns indices that has like elements before it in non-decreasing order. Non-increasing. So actually, I don't need a queue. I just need to keep track of what was the last thing and like how many things were there. So counter C shorter type. So we want non-increasing order, so it has to be K couldn't be 0, so like this should be +1, which never happens, so can skip this. So those two cases are the same, otherwise might do. So we don't care about this present number, so we should be like appending to answers here. So if it's smaller, we reset C to 1. Proof equals X. Right? So this is like the reverse of the negative. Why is it like 5 and 6? So I don't need to take the negative, just need to reverse it. Do I have something wrong? Non-increasing. If it increases, we break it. Otherwise, we... I'm a bit sleep deprived. Didn't click it. Okay, so we have undirected edges. How many people have cast? A good path. So it's a tree, and a good path is where start and end has same value. And we don't have like those with greater value in the path. Number of distinct good paths. Spurs are counted at the same. So we have one path for each node, as it's said here. So the good point is that like from one, the easy thing is that from one node to another, there's only one path. And then we cannot really, what am I saying? We cannot really iterate through all combinations of start and end node because that would be too much. But what we can do is that we start from the node with the largest value and do it recursively. Like it breaks the tree into subtrees where there's no valid path in between. But then the question somehow is like, what if we have multiple max values? Then we get like a combination value in the answer, and we again break it into subpath, subtrees. So we can either create trees at each run or find a way to indicate like what subtree we're considering. That means like, okay, we can, like how do we describe part of a tree that's not a subtree? That's what I mean. When we do the recursive function call, we cannot pass in a complete description of the subtree because that would be too large. But we can remove some of the edges from it. Then we still need to be able to compute like the local max fast enough. So there are some other ways to do this, if not by like recursion. Some kind of DP, or when we traverse a subtree, what we really want to consider is like for each node, we can consider how many paths goes through this nodes. So once we see something smaller than or equal, like smaller than or equal to it, no. Once we see something smaller than the node, any path doesn't go through here. So my initial thought when I saw this problem is that some kind of tree DP, not exactly DP, just like while moving along an edge, we carry a set of active paths in an ordered container or anything where like we have this many paths whose value couldn't be higher than something. And then while going to a node, we increment some of it and we remove some of it. Like we would be adding new path going out of this new node, and we would be removing the path that we brought here, among which like we would be removing those paths whose maximum possible value is smaller than this new node. But it's, again, like it's not clear how to implement this, what data structure I could use. Is there some other way to do this? What if we start from the smallest nodes and build a tree out of it, like step by step, initially when we only have like the smallest possible value? There can be like whatever edge we have is what goes between them. So we can sort the edges by max value at its endpoint and then gradually add edges. And for each edge we add, the path we're adding is, what am I talking about? So what I'm thinking is that for each edge we add, we're adding the new path that like so what I'm actually doing is adding nodes to the graph by increasing order, and we add an edge whenever like both nodes are present. And then at each step, we can add some good path to our answer by knowing that how many endpoints are like interconnected. Can I use a union find for that? So I union the points by our newly created edges, and then we iterate through these points to see how many of them are in shared components. So that's two paths for each point. It works, but I need the union find template. For that, I'm going to break the video. Okay, so I have my union find template here. Connected components is accessible. I would need a size. I don't need a size. Okay, so what am I doing again? Apparently, I'm going to work with indices. And I'll build the adjacency graph by only appending like outgoing decreasing edges. That means like edges that go from a higher or equal thing to a smaller or equal thing. Right. So now value 1 is greater than or equal to 2. And yes, I need that. I really just love group by function. I need list. I don't need list, but I can still use list. What? Do I need the actual number? I don't need the actual number. I only need to know. In any case, I can recover the actual numbers very easily. The correct number of parentheses, yes. Okay, now so for each group, there are 2 steps. There's a build graph step. Count different components. Step. For the build graph step, we're like that's it, I believe. I do this. So this would be a dictionary from node to its root. Actually, from root to its node. List or set? List. And then am I using K for a second time? No. I don't need K. I only need values. L times L minus 1 divided by 2. I believe that's correct. Sure. Okay, so what's wrong? In the first step we have this, and the second step we have this. In the first step we have nothing. In the second step we have this 2 things. We also need to add the single nodes. Plus, plus, plus. Amazing. Let's see. It's also interesting that I didn't wrong answer at all today, I think. Nice. Thank you.